Okay, hi everybody. So part A, why can't we use gradient descent to minimize g restricted to the unit circle, namely all the solutions to this equation? Okay, so for part A, first actually I'll draw a picture. So here's the constraints. So I'll label it constraint set of all the xy satisfying x squared plus y squared equals 1. Okay, and if we have some point here, like right there, and let's say the gradient of g at that point points that way, then minus the gradient would point this way. Okay, but either way, the gradient is telling us to leave the circle. It's telling us to leave the circle. And so I'll put that in words. Why can't we use gradient descent to minimize g restricted to the unit circle? Well, so even if our initial point, our initial guess, p equals x comma y, satisfies x squared plus y squared equals 1, which is, the constraint, satisfies, even if our initial guess satisfies the constraint, gradient descent, why can't we use gradient descent? Well, gradient descent will tell us to leave the solutions, or the solutions to x squared plus y squared equals 1, or, to leave the constraint set. Okay, but so that's why. So even if our initial guess satisfies the constraint, gradient descent will tell us to leave the constraints. But constrained optimization wants to solve the harder problem of finding an argument that also satisfies some condition, some constraint. To solve the harder problem of finding argument that satisfy, or really finding argument among just the points satisfying the constraints. So this is a much harder problem. Okay. Part B. Well, if we can't use gradient descent, then we better be able to find critical points by solving equations. And so what are critical points for constrained optimization? So I'll say in words. Well, actually, first I'll draw the picture, and then I'll explain. So at the point P, we have the tangent space, okay? This is in this case, the constraint is a curve, so the tangent space is the tangent line. So tangent space, okay? And maybe I'll even label it up here, tangent space. And then what I'm gonna do is I'm gonna project the gradient. So this is the vector w, and this is the projected gradient. Okay, well, it's projected onto the tangent space. So now let me say, what is critical points for constrained optimization are those points, are those p equals xy that, or let's say, whose projected gradient is 0. Is the 0 vector. Okay, and so, critical points for easier optimization problems, critical point means the gradient is 0. But we can't just use the gradient, it's going to tell us to step off the variety. So we have to use the projected gradient. Sorry, step off the constraints. So we have to use the projected gradient. And that's why we care that the projected gradient is a 0 vector. That means we have a chance. So right here, it's pretty clear that P is not a critical point in this picture because the projected gradient is an actual vector. It's pointing somewhere in the tangent space. If the gradient were here at 90 degrees, the projected gradient would be the 0 vector, and then we'd be at a critical point. So interesting. Okay. So now I have to say, what is the projected gradient? So the projected gradient is project the gradient, well, project it where? To the tangent space. So project the gradient at P to the tangent space, TP of C, where C is the constraints. Okay. That solves B. Now part C. Explain why non-critical points cannot be argmin. Well, let's do that. So, see, non-critical points have W equals the projected gradient equals some non-zero vector. And this means there are nearby points that satisfy the constraints and have smaller function value than g of p. So if we're at a point P, like here in the picture, and it's non-critical, why is it non-critical? Because the projected gradient is a non-zero vector. Then what this means is that we should move this way, roughly, in minus the projected gradient. And yes, that's going to take us off of the constraint set. We're going to leave the constraint set, but because the tangent space is a very good approximation to the constraint set near P, what this actually means is that there really is nearby points. All of these points here will have smaller function value. So at the point P, the function we're trying to minimize has some value, g of p, and nearby there will be other points, let's call them Q, with g of q less than g of p. In other words, with smaller function value. Okay, so that's basically it. Interesting. Non-critical points have w equals the projected gradient equals some non-zero vector. Maybe this is sort of a formula. I mean, it's not really a formula entirely. Certainly the constraints are a formula, so I should make those into the color for formulas. And I've labeled a picture, and I've described what's going on. Here's another solution. Let's see how I did from my earlier solution. So I was quizzing myself, right? First I solved this, and then I went to a blank sheet of paper and tried to solve it again without looking, and that's what you just saw me do. So this is how you should study. Study by quizzing yourself. And soon all of the stuff will be like second nature, and your mind will be free to think about how to apply this to your problems in science.